Today I want to talk about quantum tunneling in a little bit more detail. So quantum tunneling, or since we are going to solve the Schrödinger equation, we are just going to take a so-called barrier potential. So we have to specify u of x. So u of x in this case is going to be u naught if x is in between something like 0 and, let me call it a because it's easier to write, and 0 otherwise. Good. Yes. Can you say? Yes, I will. So let's first write down equations, solve equations, and then look at them, and then discuss what they mean at the end. Right? I think it's a little bit more motivating that way. But let's see. So this thing is going to be something like that. I have 0 here and 0 there, and there is like a region, maybe something like that. Let me do it. So this is, let me pull it down. So this is u of x. So for potential, I notice I sometimes use u, sometimes use v. Sorry about that. I don't think it's like there's like a universal ladder for potential. So, but when I write it, I say it is the potential u. So maybe that may help you if you get confused. So this is u of x as a function of x. So this is x is equal to 0. This is x is equal to a. So this is here u is equal to 0. This is u naught. Okay. And so to understand this problem, we need to solve the Schrödinger equation. Schrödinger equation is minus h bar squared over 2m d squared dx squared psi plus u of x maybe. So this is psi of x, this is psi of x is equal to e times psi of x. So as last time, we have to make a choice about the energy, and for the tunneling problem, we are choosing the energy to be like this. Right? We could also choose it like this, and it would be a so-called scattering problem, but at the moment, we are just going to consider so-called tunneling problem. So this is E is less than U naught. And of course, E is a positive, right? There is like a, so this is 0. E is bigger than 0, but smaller than U naught. And so, like last time, we have to solve it in 3D regions. So this is region 1, this is region 2, and this is region 3. So in region 1, in region 2, and region 3, we have to consider the Schrödinger equation separately and solve them with appropriate substitution. So in 1 and 3, we just have this equation, but u is 0, so I can erase this. And like last time, we are just going to rearrange this. So this is going to be 2m h bar squared, and we are going to put a minus here, and I'm going to erase this, and this is double prime. And this object, which is positive, right? So this is like a positive quantity. I call this k squared, or I can take the square root and say k is equal to this, and this is k squared here. And so this is the second derivative, and what are the solutions? We know by substitution e to the I kx is a solution. So this is what we called right mover, and e to the minus I kx is also a solution. This is what we called left mover. Okay. Basically here in region 1, maybe I can write it here, we have a e to the I kx plus b e to the minus I kx. And here, let me call it ab. I will use c and d for the constants here, so I'll skip e because of its energy. F e to the I kx plus g e to the minus I kx. So these are the most general solutions in region 1 and in region 2. So I have to solve it in region 1 and 3. Now I have to solve it in region 2. So it is exactly the same equation. So I copy that. So for u, I'm going to put u naught. And I take u naught to the other side. So it is going to be, like last time, u naught minus e is equal to, and there's like an overall minus. And this overall minus is going to cancel this one. And I'm going to write this 2m over h bar squared here, erase this, and erase that, and double prime. And this thing is going to be what we call alpha squared, or I'm going to take the square root, and this is going to be alpha squared. What's that?
H bar squared.
Yes, h bar squared, thank you. And the solutions for this is like solutions. You can choose either like e to the I kx, e to the kappa, e to the minus alpha x or e to the plus alpha x. Solutions are e to the alpha x. Put this a little down. And e to the minus alpha x. How do I know this? By direct substitution, like last time. If you take one derivative, it is alpha. If you take one more derivative, it's alpha squared, and it is like a positive quantity, so it satisfies the differential equation. And same for minus alpha. Then here in this region, I'm going to call it c e to the alpha x plus d e to the minus alpha x. So this is the differential equation, but as you remember, in the Schrödinger equation, we have to solve a differential equation satisfying a given boundary conditions. And now we have to think about boundary conditions. And maybe you may have figured that out. Every problem requires a unique definition of boundary conditions. For example, in the case of a particle in a box, we had like a wave function amplitude vanishing at the walls. In finite well, that wasn't the case, but the wave function and its derivative was continuous. Now this problem is completely different, so we have to think about the boundaries in a different way. And here's how I think about this. So I want to set up the problem so that if I send a wave from here with unit probability, and I put my detector to here, what is the probability to detect an electron, right? The problem is I send the electrons from here with the given energy, which I can decide, which I can tune k. I send it. It may or may not pass through the barrier, but I put my detector here and look at the probability to observe it. But this problem says what? I am sending a wave. So this is 1, because wave function is probability, and if I know I send it, I'll just take it 1. And now this B is going to be what we call reflected wave. and I look at on this side, and I have on this side a right mover and a left mover. But if I send it from here, what comes out and just goes on, right? If the source of the wave is here, there shouldn't be any left movers on that side. So I am going to cancel this one. So this is 0. So they can only be a transmitted wave on the right hand side. So I am the one who is solving the problem, right? Like you will be in like exams or homeworks or later in your career. You decide, right? You decide how you set up the problem, and this is how I set up my problem. So, and in the previous case, in the finite well problem, we were saying that wave function shouldn't blow up at the infinities, right? That was like a different setup. Now I have, like even at minus infinity or plus infinity, I have a finite amplitude because I am sending it, but there is like a different boundary condition that I need to consider. So this is the first thing. Now let's put the continuity of psi and psi prime. So psi 0 should be continuous. What this means is e to the I k a plus, this is 0, 1 plus b, right? E to the I k times 0 is 1, should be equal to c e to the alpha x plus d e to the minus alpha x, but x is equal to 0, so it's going to be 0 and 0. Yes?
Why we didn't cancel B? Because it's also left.
But it can just hit barrier, right? So there is no left mover here because there is no barrier to reflect from, right? Whatever passes through is going right, like it's going to the right. But in this case, there can be left mover here because it can reflect from the barrier. Yeah, that's a good point. Thank you. Similarly, we need to look at the derivatives. So psi prime 0 should be continuous. On the right hand side, I have ik. Let me actually keep a also. Right? Yes.
I didn't get why we choose x is equal to 0 for the second solution.
So here, I am right now looking at the boundary condition here. Right? So this is x is equal to 0 boundary condition. And there will be two boundary conditions coming from here, and there will be two coming from here. And I think it is nicer to keep track of the terms in my equation. So I know I will take a is equal to 1, but I think it's a good exercise to keep it as it is. So let me write a so that I can keep track of this term. So the second one is going to be derivative. If I take the derivative, there will be like an ik times a, and if I put x is equal to 0, there will be just 1 minus ik b, because this is the left mover in the second case, should be equal to c alpha minus d alpha. So this is the first pair of boundary conditions. Now let's implement the same thing for psi of a should be continuous. What this means is a e to the ika plus, this is ab c e to the alpha a plus d e to the minus alpha a should be equal to a, b, c, d, e, f e to the I, k, a. And when I take the derivative, I'm just going to pull down these like factors in the, like this is going to be alpha, there's minus alpha, and there'll be ik here. Yes?
When we set g e to the negative ika,
0.
goes to 0. Is it because the wave goes from left to right?
Yes, it goes, that's my setup. Like imagine you are sending the wave from here, right? You are the one who is shooting,
Yeah.
and you put the detector here, and there's no other source. For something to go to the left like this, right? It either has to reflect from something which it doesn't exist, or there might be another source, but we don't consider those things. So there are like now these 4 equations that we need to solve. So let me rearrange. So this one is going to be, let me pull this a little bit. So this is alpha C minus D. And I want to divide it by IK and raise this. And if I sum these two, right, sum, I'm going to, B's are going to cancel, and I'm going to find 2A is going to be equal to, there's like one C coming from here, another C coming from here. It's going to be 1 plus alpha over IK C plus 1 minus alpha over IK D. Okay, so this is, if you want, I eliminated one arbitrary coefficient B. Now I want to do exactly the same thing for this one. So let's divide with alpha and erase this one and this one. So if I sum this one and this one, you can see these first terms are going to cancel. So this is going to be 2C e to the alpha A, 2C e to the alpha A is equal to 1 plus IK over alpha F e to the I KA. And if I take their difference, 2D e to the minus alpha A is equal to 1 minus IK over alpha F e to the I K A. Good. Now I can plug this C to here and this D to here, and you can kind of see, right? This is A, there's like C and D, but when I do the substitution, there's only F and F. And at the end, I want the transmission amplitude, and transmission amplitude is going to be A divided by F, and all arbitrary coefficients will be eliminated. So let's now do that. So this is, let me just copy this equation. So let me pull this down. So this C then is going to be equal to minus alpha A, and this is 1 over 2. So this is my C. Then I can put entire thing here and erase C. Good. So unfortunately we have to do these things. Nobody likes this. I hate to do it every time, but I have to do it. And you also have to do it because, you know, you took this course yourself. Nobody forced you to be here. So the second one is alpha A. Erase this. So this is 1 over 2. This is D. And now I'll erase this D and put this D here. Good. And now I can take these two and write 4 here. Let's try to simplify things a little bit. And I can take this e to the ik to here. This is e to the minus ika. So this guy is gone. And this guy is gone because I took it to the other side. And I want to divide it by f. This one is gone. This one is gone. And let me squeeze it a little bit so that we can see everything in one line. Okay. And I think we are okay. Now I look at this. So this is 1 plus ik over alpha plus alpha over ik. So i's are going to cancel, plus alpha k divided by alpha k is going to be 1, right? And similarly here, so this is 1 minus ik over alpha minus alpha over ik. So minus minus plus, i's cancel, k's cancel, alpha cancel, this is also 1. So let me write this and let's see what we can do with this. This is going to be 2 plus, I also multiply this. This is going to be minus k squared plus alpha squared. Divide the entire thing with I alpha k. Correct? Yes. And this is e to the minus alpha a plus, so the same thing, 2 minus k squared plus alpha squared divided by I k alpha e to the alpha a. So, okay, now here is this result. Now let's think about what we need. The goal is to find the transmission probability. What is the transmission probability? T, let me use T for this. It's equal by definition to current transmitted current. So this is particle current. So you can think about density current but without the charge, and divided by J incident. So maybe from, I can ask you, what is the definition of a current in electricity and magnetism you learned last year? How do I write current? If you want, you can also put charge in terms of density and velocity. Current density written in terms of particle density and particle velocity.
Are you asking what current is?
Yes, the current density J in terms of particle density, particle velocity. If you want, you can also consider charge current.
The amount of charge passing in time and in a surface
Uh-huh.
and area.
Yes, what is the expression? Right?
You can say Q over
Mm-hmm.
T, and assuming an area, you can show it with A.
Yes. So what should I write? There is like an expression, right? You write the expression and you manipulate. What is the expression? So I give you the density, I give you the velocity. If you want, I can also give you the charge, but we are not interested in charge current, we are interested in particle current. So how do I combine these two things to form current? N times V, right? Yeah. So this is N transmitted times V transmitted divided by N incident times V incident. So what is N transmitted? What is the density? We have the wave function psi. What is the transmitted? Right? Based on the Born interpretation of quantum mechanics, what is the density N of T in terms of psi? Psi squared, right? But psi squared for the transmitted is only, in our problem, there's only F. And if you take the psi squared, it's going to be absolute value of f squared. So this is absolute value of f squared. What is the velocity? So you answered, so what is the velocity in terms of k? What is classical velocity in terms of p? So nobody in this class knows what v is in terms of like a classical momentum. P over m. But in quantum mechanics, what is p? We have k, right? H bar k, right? So then this is h bar k transmitted, but there's only one k, so I don't need to write it. Divided by m. Divided by, I'll do exactly the same thing. Incident is amplitude a squared, and I have h bar k over m. So these all cancel. So at the end, my t turns out to be f over a squared. And that's what I'm interested in. But I have, you can see here, something, right? A over f. So let me take the absolute value of both sides and then see where is
B.
I eliminated b, right? So I, like here, I wrote these equations and I said, let me eliminate b by summing these two. And I eliminated c and d, and there's no a, b, c, d in this equation. So that was the whole point of doing this messy calculation. Uh-huh.
F and A stand for psi 2, right?
So f is transmitted amplitude, right? Wave, the transmitted wave's amplitude is f. So the coefficient f e to the I kx on the right hand side, and a is incident a times e to the I kx on the left hand side. So that's why it's good to keep the coefficients so that you know which term you are working with. Now let me collect, so here's everything I need. So I'm going to take the absolute value here, and it is going to give me, let me copy this entire thing and manipulate, maybe here. Actually, let me copy this. So this is one side, and on the other side I have, what was it? Square of e to the ika is 1, square of 4 is 16. I have here 16 a over f squared. Okay? And a over f squared, when I invert it, is exactly what I need. So you can, yes. Oh yes. Sorry, I'm going to take the yes. Square. Thank you. So to do this, I am going to do the following. So yeah, this may look like a messy expression, but at the end of the day, it is going to be some real part plus I times imaginary part, and absolute value of this thing is going to be x squared plus y squared. Okay, this is just a little bit simpler to do. And then let's do that. So this is going to be, let's write the real part. Real part is, you can see 2 e to the minus alpha a, and there's another one here, plus e to the alpha a. So this is the real part. And you can see these terms are also identical, so let's combine them. Plus minus k squared plus alpha squared divided by I alpha k e to the minus alpha a. So here is plus, here is minus, so this is going to be minus e to the alpha a. And I'm going to take the absolute value square. Yes, I think that's correct. This one seems to be correct. Okay, good. But this I, So I want to write it the other way. I want to put it minus, and I want to put this one plus, this one minus. Because I'm going to write like cosh and sinh for these things. So this is the sinh and this is the cosh part. And for I can multiply both numerator and denominator with I, or with minus I. And minus I going to be plus I here, and this one is going to go. Now I can do this, what I said. So here, let's first write this. This is 2 hyperbolic cosine alpha A. And this is 2 hyperbolic sine alpha A. So if you don't remember them, we generally give these, and or you can, if you are working yourself, you can just look at Wikipedia, right? I don't expect you to memorize these things. Then now I can take the square, so the square of the first piece is like 2 times 2, 4. If I take the square, it's going to be 16. This is cosh squared alpha A. And the second one is plus alpha squared minus k squared divided by alpha squared k squared. And I feel like I missed this factor of 2. This is also going to be 4 squared. Okay, right? This is, I think there is no, there's no 2 here. This is going to be 4 sine hyperbolic squared alpha. Okay, so let's cancel this 16 with this, and this is going to be 1 over 4. And for cosh, this piece, I'm going to write it like 1 plus sine hyperbolic squared alpha A. Again, I don't expect you to memorize. If you remember this, that's good. But if we happen to not give it to you, you can ask, and I can write these things on the board. I don't expect you to memorize these things. If you are scared, take it easy. This is not a big deal. So this thing is going to be equal to 1 plus. So there's like sine hyperbolic squared, 1 plus 1 over 4 alpha squared plus k squared. Okay, there's also squared that I shouldn't forget. So this is alpha squared k squared, close this entire thing, and this is sine hyperbolic squared alpha A. But this thing, if you manipulate, so this is alpha squared plus k squared minus 2 alpha squared k squared and plus 4 alpha squared k squared, which is equal to alpha squared plus k squared, then this thing happens to be 1 plus, let me just copy this. And there is 1 over 4 here. I think despite all these complications, we still didn't have a nice expression, but I think it is not as bad, right? It is at least compact. And t is equal to f squared over a squared, but this expression we calculated is a squared over f squared. So if you invert this, this is going to be 1 divided by this entire thing. Okay. Now I want to whenever we have something like this, like last time, alpha, k square, all these things are a little bit complicated. We want to put it in a dimensionless form so that we can put it in a computer and plot it. And to do that, I want to define these things like I defined last time. So this is first, let me define alpha times L, or alpha times A. This is going to be equal to 2m over h bar squared u naught minus e a squared. And you may have now recognized that h bar squared over 2m a squared is a unit of energy, and this thing I can write it like u naught tilde minus e tilde, where u tilde is u divided by, okay, u tilde is equal to u naught divided by h bar squared over 2m a squared, and same for e. Okay, let me write it. E tilde is equal to e divided by h bar squared over 2m a squared. Similarly, k times a is going to be equal to 2m over h bar squared e a squared. This is going to be root e tilde. Good. Then this expression, okay, so t becomes 1 over 1 plus 1 over 4. Let me write the so this is u tilde minus e squared is u tilde minus e tilde plus k squared is, so if you want, I am multiplying both numerator and denominator with a squared, and I'm putting it inside the parentheses to put it in this form. So this is going to be divided by alpha squared is going to be u naught minus e tilde times k square is e tilde, and inside sine hyperbolic I have alpha a, which is going to be root u tilde minus e tilde. Good. So these e tildes cancel. I have only u tilde, u naught tilde. And I also, okay, one more thing to define. X, I want to define e tilde over u tilde. Then I can take it to the denominator. This is 1. This is going to be x. This is going to be x. And this, I'll take it outside. So this is root u tilde. This is 1 minus x. So there's only two parameters in this equation, u naught tilde and x tilde. And we can draw this. I think I have it here. So this is exactly the function. Okay, I can zoom in. Hopefully you can see it. So this is exactly the function I entered. And now I think I need to rerun it. So this is, I can tune u tilde. You can see initially, so this is E, this is transmission probability. Initially I have 0 probability, but it seems to increase. And I change it a little bit. Maybe this one is good enough. I can copy this and show it to you. These things are, so this is x, which is equal to E over u naught. And this is transmission probability. And you can see here is like 1, 2, 3, 4, 5. And even when E is less than u naught, T is non-zero, right? We first of all seem to have like a non-zero amplitude to transmit even below the barrier. So this is not a classical observation. So this is what we call tunneling. So we are going to talk about this just a little bit more. But the second observation is like there seems to be like 100% tunneling probabilities here and there. Even though E is not infinity, T seems to be 1 here. So these are what we call, there are resonances. I don't know, what is this? Some E is equal to some E star, if you want. Now let's see why, I will finish it in 1 minute. Let's see why this is like a purely non-classical observation. Suppose the barrier is not this, but like something like this hill, right? I put this hill, and suppose you are here, and I am here, and I have a ball here, and I want to send it to you. And I want to look at the height of the hill, and say the height of the hill is U0. Classically, you know that if the ball comes to you, it has to go over this barrier. And if it's going over this barrier, it has to have at least energy of U0, right? It has to go here and then roll down, and when it comes to you, then you can say this ball has at least U0 energy. But classically, what we expect does not seem to be the case in quantum mechanics. Because even if I put energy here, which is well below the barrier, the particle may come to you. So that's the essence of tunneling. And historically, that's like a very important observation because, this is the last thing I'm going to tell, and I'm going to finish it here. So in the decay of some nuclear compounds like uranium-238 decays into something called thorium-234, and if you count like the nucleons, you are supposed to have like one extra alpha particle. So nuclear physics is complicated, but like people know how to probe the nuclear structure, and these things that you can think about these protons and neutrons, which we call nucleons, to be bound by so-called strong nuclear force. And from the scattering experiments, like you can bombard these things and look at the energy you need to break an alpha particle from this thing. And what you are going to find is like there is like a huge energy barrier. We can model this thing like this, something like that. So this is U of R. It is spherically symmetric. Any direction is fine. And this is R. And from these like scattering experiments, you know this thing is like order of, I think I wrote here, 35 MeV. And now, when you put uranium in your lab, there is like an alpha particles coming out anyways. And you can look at the energy of these alpha particles. Like for example, you put your detector at a very far point here, and this alpha particle, which is like a hydrogen atom, which is like a helium atom without electrons, look at its energy. And its energy turns out to be 4.3 MeV. And people observed this before the full development of quantum mechanics. And then the question was like, there is like a gigantic skyscraper here, like huge hill, and then something seems to be going over the top and then rolling down, but it's coming with an energy of like 4.3 eV. How come like such a tiny energy can get out of such a huge barrier? And the reason is just pure quantum tunneling. So there are many examples of quantum tunneling. It's one of the most important things and one of the most important application of quantum tunneling. In solid state systems, like there are what we call junctions are based on quantum tunneling. Atomic force microscopy is based on quantum tunneling. And but this all this like zoo of phenomena can be explained with our calculation here. Okay. So let's take a 5-minute break, and when you come back, I'll continue with harmonic oscillator.